All right. Hi, everyone, again. This is now topic 8.9, volume with something called disk method. So we have moved on from cross sections, something called disk method. So we are going to be revolving curves around either the x-axis or the y-axis in this topic. And I'm really excited about this topic. I personally love these 3D rotations. I think they're really cool, so I hope you all enjoy it too. So to get us started, just a visualization of what's happening here. We're going to graph y equals x squared from 0 to 1. And now, as best as you can in your mind's eye, imagine rotating this curve around the x-axis. So we're going to attempt to draw this 3D image as completely as possible. So if we are rotating this around the x-axis, just imagine that this curve is coming out of the paper, 3D, going back into the paper, going into my desk, and then coming around and meeting at the other end. So what it's going to look like is it's actually going to be circular in shape, something like this, around the x-axis. So now we are going to draw a slice of this three-dimensional object. So if you can imagine, we're going to take out a little slice, and we're going to draw it over here. So essentially, we're imagining looking at a coin on its thin side, and we would like to know the volume of this slice. So we have a solid slice. This is completely solid. This is a solid object here. Now, this is circular. This is circular. So it has a radius. And it has a thickness. It's just like a coin has a thickness. So we can find the volume, essentially, of a coin, of a circular object that's, say, more like a cylinder, like a really thin, flat cylinder. You're going to take the surface area of the top, the face, and you're going to multiply it by the height. This is the volume of a cylinder. So here, our height is the thickness of this slice from our 3D object. So this is actually dx, however thick our slice is here. So you'll notice when I pull this coin, this slice out, my radius is half the diameter, obviously. But you'll notice the radius here is from the x-axis up to the curve, because the other piece of it would be down below when you rotate it. So our radius here is actually whatever my curve is, and in this case it's x squared. So for this volume of this one slice, I'm going to replace r with x squared. And so you'll notice the volume will be x to the 4th, and my height is dx. And lastly, step number 4, how can I add up all the volumes together? Well, we're going to integrate. So the problem told you to integrate from 0 to 1. Pi x to the 4th dx. And you can go ahead and plug this into your graphing calculator if you'd like. You get about 0.628. So this volume is, this 3D object, the volume is pretty small. We only went to 0 to 1. So another visualization we can use to imagine this is if you imagine a fan opening all the way around. This is essentially what we have happening here with our slice. So you can see here that if I were to take this curve and open it all the way around like this, around the x-axis, it would meet up back where it started. And so this would be like a slice. This is a very thin slice of our 3D object. So you just imagine a bunch of these fans opening all at once to make a solid object. So this is called the disk method. The disk method, we will see soon something called the washer method. That is a second method to take volumes. But I called it a coin earlier. If you imagine, this could also be called a disk. That's a way to help you remember. So you'll notice the pi is here from A to B. Those are your boundaries. R squared dr, where r is your radius of your slice, and the thickness of it is dr. Let's go ahead and try a couple examples. So example 1. What is the volume of the solid generated when the region in the first quadrant, bounded by the graph of y equals e to the x squared, x-axis, and vertical line x equals natural log of 2 is revolved around the x-axis? E to the x is exponential. We know that it goes up to 1. It's going to stop at natural log of 2. So we have a very similar shape as our 3D object from before. However, this time, when you rotate this around the x-axis, it's going to have a rotation down in here. So I'm going to draw it sort of into my words in the next example, but our 3D object will look something like this. So you'll notice here the thickness is a little bit thicker here compared to up here where it met at 0, 0. So here when you rotate, you'll have something that looks more like this. So if we use our formula from above where the radius is r is the radius from the slice, if you want to draw that slice again just to get a better visualization of it, where I have drawn this centerpiece is the x-axis. So this radius is however tall the curve is at that point. So the radius is actually e to the x here. And like before, our height of our slice, this coin, this disc, is dx, however thick the slice is from the x-axis. And so we can go ahead and use this formula. Here, we were told that our boundaries were in the first quadrant, so I know I'm going to start at 0, and I'm told I'm limited by natural log of 2, so go from 0 to natural log of 2 of my radius squared dx, that is the thickness, so here my radius was e to the x. For this one, it is not calculator active, so let's go ahead and solve this by hand. Now, e to the x squared, if you recall your exponential laws, this means that you can multiply exponents. So instead of e to the x raised a second, it's now e to the 2x. So if you were to use u substitution here, which I will do off to the side here, we're going to let u equal 2x. So du is 2 dx. I do not have a 2 anywhere here, so I need to divide that out. So dx is 1/2 du. So I'll go ahead and pull the 1/2 out in front with the pi. And then if you recall the substitution, we can also substitute in the limits. So if I let 0 be x here, then u would become 0. And if I let x become natural log of 2, then u becomes 2 natural log of 2. 2 times natural log of 2. The antiderivative of e to the u is just e to the u. I'm going to continue down here. Once I plug in e to natural log of 2, I would subtract away e to the 0. Now, if you recall your natural log rules, this 2 here can be brought up as an exponent. So 2 squared is 4. E to the 0 is 1. So here e and natural log will undo each other. So I have 1/2 pi 4 minus 1, which is 3 pi over 2, which is answer B. Okay, this next one I'd also like to do with you. We have a triangular region in the first quadrant with vertices at 0, 0, A0, and B0. Sorry, that should say 0B. I apologize. Typo. 0B. Where A and B are positive constants, which of the following gives the volume of the solid when it is revolved around the x-axis? So as always, I prefer to have a sketch. So we have a triangular region from 0, B down to A, 0. So if you imagine rotating this around the x-axis, this one again will look maybe like a sort of megaphone, I suppose. So again, we're taking this, we're rotating it around the x-axis, so it's going to be somewhat like a pyramid on its side. So if it helps, you can maybe flip the paper over, you can kind of see a pyramid. So now you'll notice we need to find the radius of our slice. So if I draw this slice here, I actually don't know how high it is from the x-axis to the curve, so I need to find it. So this is a piece of a line. So I'm going to find the slope and the y-intercept. I know the y-intercept is b. The problem told me it was b. And now I can find the slope. And if you use slope formula, you can do 0 minus b over a minus 0. So you get negative b over a. So then this line becomes y equals negative b over ax plus b. So this is slope formula with the y-intercept to make the equation of this piece of the line. So I actually found my radius. So again, using the formula for disk method up above, pi goes from 0 up to a. Those are our boundaries on the x-axis. And then whatever my radius is squared, and my thickness is dx. So here I will have negative b over a x plus b. And you will notice that is answer C. So all the other ones, there's something slightly, I'm sorry, answer D, I apologize. There's something slightly off about them. A and C have the limits going from 0 to b, so that's off. And then in answer B, it doesn't have the negative that we need. Last example on this page, go ahead and pause the video here and solve it for yourself, and when you click play, I will go over it. So in this example, we have a solid created by y equals 2x, the x-axis, and the vertical line x equals 3, when it is revolved around the x-axis. So again, imagining this rotating around, or if you'd like, imagine this idea of a fan. So a fan opening up something like this, but it would be a lot thicker than just this thin fan here. So you have something shaped like this. And so if we want to pull out a slice to see the radius of the slice, again, where I draw the center of this slice is the x-axis, and the height is however tall the curve is. So this curve is 2x tall. Using the formula for disk method, pi from 0 to 3 of 2x squared dx. And you'll notice this one, you cannot use your graphing calculator, so we will practice doing this by hand. If you multiply it out, you get 4x squared. The antiderivative of 4x squared would be 4x to the third power over 3. And when you plug in 3, you get 4 times 3 to the third over 3. When you subtract out, when you plug in 0, it would just become 0, so I'm not even going to write it. So at this point, there's 3 3's here that would be multiplied out. Divide out with one of the 3's here. You would end up with 36 pi. All right, go ahead and click on the next video for the backside.